Hello everybody, this is Dr. Christopher White and welcome back for part 2 of plate tectonics. So if you remember in part 1 we had just been discussing the evidence that Alfred Wegener used to come up with his model for plate tectonics. We also touched on the fact that although the evidence was very convincing, there was one minor problem. He didn't actually manage to explain why the continents actually moved. He showed good evidence to say they were once linked together and then split apart. He didn't actually have any mechanism to say why they moved apart. So what we need to do now is we need to come up with that evidence to show the continents were moving apart from each other and also explain why they're moving apart from each other. So the next step in the process occurred in 1962 when Henry Hess wrote a book called The History of Ocean Basins. Now, Henry Hess had been in the US Navy and he had spent a significant amount of time in the Pacific. And so whilst in the Navy, Hess made two observations which were key. The first observation he made was that he noticed that the oceans are shallower towards their centre along ridges that sit up to 1.5 kilometres above the ocean floor. So if you were to go into the middle of an ocean and look around enough, what you would find is there would be this ridge, this linear body of elevated terrain that ran through the centre of your ocean. The second observation that he made was what the deepest parts of the seafloor were located where we have continental crust meeting oceanic crust. Of course, the most extreme example of that is the Marianas Trench. Okay, so the Marianas Trench is about 11 kilometers deep, give or take a little bit. So he made these two observations. And so what Hess went and envisaged was, he thought, well, right, maybe new crust is being created at the ridges. So he thought maybe the ridges, these areas of seafloor, were being pushed up because there were huge amounts of magma underneath them. And magma is hot, it's buoyant, it wants to rise. And so it pushes the crust up. And so, okay, that would mean the ridges are where new oceanic crust is being made. And then obviously that, as new oceanic crust was made, it would cool, solidify, become rock. That rock would cool down. As it cooled down, it would become denser. And then that dense rock would slowly move down the sides of the ridge and away. And obviously new magma would then rise up to produce new crust. So that was his explanation for ridges. Now the thing is if you're creating new crust at the ridges, well, that means you obviously have to destroy the old crust, because if you didn't, the surface of the Earth would just keep getting larger and larger and larger. So the next question is, well, where's the old crust being destroyed? And the answer is the old crust is being destroyed at these trenches. So Hess's next idea was that as the oceanic crust was pushed away from the ridge, it would move laterally, but eventually the oceanic crust would hit something like a continent. And when that oceanic crust hit the continent, it would be pushed down underneath it. And so that oceanic crust would be pushed down into the mantle, where eventually it would melt and be destroyed. And the point at which this oceanic crust is being pushed down under the continental crust would produce these trenches, these big, deep, linear, essentially trenches in the seafloor. So if we look at the Pacific, what can we see? Okay, I've marked out the ridges in red and the trenches in yellow. Now they're a bit difficult to see, but you can see them. So these red lines here will represent areas of the seafloor that are about 1.5 kilometers above the ocean floor either side. So if we look at this diagram down here in the bottom right, we can see here is a very stylized diagram of a ridge. Okay, so the ridge will be about 1.5 kilometers taller than the seafloor either side of it. And so as Hess was suggesting that we have magma underneath the ridge, that's what's pushing it up, making the ground rise. And that magma would then also rise to the surface, producing new crust. Okay, Hess's model then said the old crust would cool down, it would slide down the side of the ridge and then be pushed laterally over time. As new crust is made over here, it pushes the old crust laterally, and that old crust would move laterally until it eventually reached a piece of continental crust, and when it hit that piece of continental crust, the oceanic crust would then be forced down into the mantle. And that process of pushing the oceanic crust down into the mantle would create this trench. And if we look over here, we can see in yellow we have the trenches. So for instance, if we look at the Nazca plate here, the model would be new crust was being made at the ridge here. The new oceanic crust was being pushed away from the ridge, so it was moving eastwards. And then that piece of oceanic crust would eventually hit South America, and it would be pushed down underneath South America into the mantle, and that movement of the old oceanic crust underneath South America would produce the trench that we can see here. And so that was Hess's model, and it's brilliant. It's a wonderful use of the evidence that he can find and some good solid geologic thinking to essentially explain what he could see. So wonderful evidence to back the process of plate tectonics. It suggests that new crust is being made, old crust is being destroyed. Okay, now this gives you a push, doesn't it? So as new crust is being made at the ridge here, it's pushing the old crust away from it. All of a sudden you have a pushing force now, don't you? Which can start to make the continents move. So everything's looking really good. Problem is that it still doesn't actually give a mechanism. It doesn't explain, well, why is there all this magma underneath the spreading ridges? So it's getting there. We've taken a step, but it's still not the complete picture. Okay, so Hess was then followed by Frederick Vine and Drummond Matthews, and they published a paper in 1963 called Magnetic Anomalies over Oceanic Ridges. So Vine and Matthews were focusing on the North Atlantic this time, so they weren't in the Pacific, they were dealing with the North Atlantic. So what they noticed was that if you looked at the magnetism of the seafloor rocks, as you went from Europe to North America, you would actually see that the magnetism, the polarity of the rocks, would flip. Sometimes the magnetic polarity would be positive, and sometimes the magnetic polarity would be negative. Okay, so the other thing they noticed was that you saw a mirror image either side of this ridge in the middle of the Atlantic. So if we just go to the next slide, nope, of course I didn't put the picture in there. That would have been helpful if I did, but I didn't. So what Vine and Matthews spotted was that you had this ridge in the centre, just like Hess had said, there would be, and that as you moved away from that ridge, you could see these repeated changes in magnetic polarity of the seafloor rocks, and the magnetic polarity would change in a consistent way either side of the ridge. Each side of the ridge would mirror the other. And so this would suggest that new crust was being created at the ridge, and then that new crust was being split in two, one half going west, one half going east. And then new crust would be created. That piece of crust would be split in two, one half going west, one half going east. And whilst that process was taking place, every once in a while, the magnetic polarity would change. And so we can see those changes in the rocks. Now, don't worry about this too much. In a few slides' time, we're actually going to look at it in greater detail, and it's going to become a bit clearer, hopefully. So also in 1963, Tuzo Wilson went and proposed the idea of hotspots. So if we look at the North Pacific, what we can see is we have the Aleutian Trench here. Okay, once again, Henry Hess was suggesting that this is where the oceanic crust is moving northwest, and it's then subducting down underneath the continental crust here, and this trench here represents the point where the oceanic crust was subducting underneath the continental crust. Now we can see along, well, you might know that along the Aleutian Trench here, we have the Aleutian Islands, which are a line of highly volcanic islands that run from Alaska all the way over to Russia. Now, another thing that Tuzo Wilson noticed was that sometimes, yes, you get these chains of volcanic islands, and they're normally associated with these trenches. However, every once in a while you would get a chain of volcanic islands, like Hawaii, that would be in no way associated with a trench. And the other weird thing is that when you looked at these chains of volcanic islands, you could see that they were linear. Note the trench here has a curve to it. Where we have oceanic crust subducting underneath other crust to create a line of volcanoes, it's very common for those lines of volcanoes to have a slight curve to them. Okay. In the case of these linear bodies, you can see the volcanic islands line up in a straight line. So what Tuzo Wilson went and suggested is that, well, maybe there's a big ball of magma located right here, stuck underneath the oceanic crust. Now the ball of magma doesn't move, but the oceanic crust does. And so as the oceanic crust moves across the magma, moves across this big ball of magma, some of the magma will rise to the surface and create an island, and then the island will be pushed off towards the northwest. And then obviously as that island moves in the northwesterly direction, a new island will form, and then that island will move towards the northwest, then a new island will form, and so on and so on. And so by looking at these linear chains of volcanoes, all of a sudden Tuzo Wilson went and said, well, this is even more evidence to show us that the seafloor is moving. Okay, so he's saying these hotspots represent a stationary point that does not move, and the lines of volcanic islands that form above these hotspots are the result of the oceanic crust moving over the top of them. Now, Tuzo Wilson then went even further, because what he realised was that Henry Hess was right. New crust was being made at the ridges, and it was being destroyed at the trenches. However, there was a problem. There was always going to be a situation where you couldn't actually get crust to either subduct, so be destroyed, or make new crust. There were going to be occasions when crust simply had to move past each other. And so when he realised this, he had essentially come up with the third type of plate boundary, which is called a transform or a conservative plate boundary. And this is simply where two pieces of crust just move past each other. No crust is made, no crust is destroyed, it's just conservative. The pieces of crust just move past each other, nothing really happens. Of course, the classic example of that is the San Andreas Fault, where you have essentially the western part of California is moving in a northwesterly direction, whilst the other side is moving in a comparatively southeasterly direction. So okay, so we've had Alfred Wegener came up with a model. Henry Hess began to get, really start to show the mechanism. He, came up with the idea that new crust is made, and as that new crust is made, it pushes old crust laterally, and that starts to give you that push that it begins to explain why the continents are moving. Then we have Vine and Matthews coming along and saying, right, we have this evidence from the spreading ridge in the middle of the Atlantic that shows that new crust is being made and being pushed laterally, so they're backing up Hess. And then Tuzo Wilson comes along and says, right, these chains of linear volcanic islands, they also show us that the crust is definitely moving. So once again, this is showing us the ocean crust is in motion, and that's obviously going to start pushing the continental crust. And then obviously Tuzo Wilson follows that on a couple of years later by saying, okay, I also, I'll come up with the idea of transform plate boundaries, and that will allow pieces of crust to move past each other, because sometimes you can't destroy crust and sometimes you can't make crust. But it still doesn't quite explain what the mechanism is. What's the driving force? That was explained in 1966 by a gentleman called Dan Mackenzie. And what Dan Mackenzie went and did is he went and took several different disciplines and combined them together. So he combined radioactive decay, thermodynamics, continental drift, and magnetic anomalies to produce a robust model for mantle convection. So what Mackenzie realised was that the Earth's internal heat was causing the mantle to convex, just like water convects when it boils in a pan. So the hot mantle would rise, cool down, and then sink, and you would get essentially a circular convection going on. Now, the thing is as the mantle comes up and then it moves laterally, drops down, and sinks again, you're essentially creating a pull, aren't you? So because the mantle is moving, it's going to try and pull the crust, which is on top of it, along with it, isn't it? And so all of a sudden you begin to have the first stages of what is allowing your mantle, what's allowing your crust to move. So Dan Mackenzie answers the question. So it took to 1966 to actually come up with a definitive mechanism that explained why the continents were actually moving, but it was eventually done. So now let's go back to those magnetic anomalies. So as I was saying, if you take a magnetometer and you pass it over the seafloor in the North Atlantic, you'll very quickly see that the seafloor doesn't have a consistent magnetic polarity. sometimes the polarity is positive and sometimes it is negative. We're going to have to explain why that is. So to begin with, the Earth's magnetic field is the result of convection, result of the convection of the Earth's liquid outer core. So if you remember, the outer core is made from iron-nickel alloy. That's convecting, and in the process of convection, it creates very, very strong electric currents, which lead to the formation of a very powerful magnetic field. So when we think of the Earth's magnetic field, we think of it simply like a bar magnet. We have a northern end and a southern end. Okay, and if we put a magnet like this on a piece of paper covered in iron filings, we get these things. Okay, now these are lines of magnetic force. These are showing us essentially the lines along the path along which the magnetism is moving. And so the question is, well, does this apply to the Earth? And the answer is, well, yes, it does. So the strength of the Earth's magnetic field varies slightly with latitude. So the closer to the poles you get, the Earth's magnetic field will vary ever so slightly. The other thing that will change is the angle at which the magnetic field intersects the Earth's surface. So if you look at this diagram here, you can see the angle at which the force lines are intersecting the Earth's surface changes as you approach the poles. It becomes steeper, doesn't it? So we can see these force lines, which we can see here in this picture, also occur on the Earth because we can measure the changes in the angle of the magnetic field as, well, in rocks. So the question is well, why is this important? What does this, really help us with? Well, it doesn't help us until we see this. Okay, so this is some of the evidence that was found, when you pass a magnetometer over the North Atlantic. So this area here represents an area of the seafloor, and you can see you have these black and white stripes. In fact, it looks a little bit like a zebra. So the black lines represent positive magnetic anomalies, and the white lines represent negative magnetic anomalies. Okay, so what does this mean? Well, I'm sorry, we're going to have to do a little bit more detail and then we can begin to tie it all together. So one of the things that iron oxide minerals do is that they can take on the magnetic field of the Earth when they crystallize. So if you have an iron oxide mineral, now the most common iron oxide mineral that we use for this is a mineral called magnetite. Okay, so let's say you have a crystal of magnetite. That magnetite crystallizes from a magma, and the crystal of magnetite is happily floating around. Everything's going well, nothing particularly interesting is happening, cooling down. Well, when that crystal of magnetite hits 580 Celsius, it will hit what's called its Curie point. And at that moment, the magnetite will lock in the orientation of the Earth's magnetic field at that time. The Earth's magnetic field will actually affect the mineral, and so that signature will be retained within the crystal. Now, basalt, the stuff that makes up the seafloor, has loads of magnetite in it. So there will be trillions of magnetite crystals that are forming, and they will all take on the magnetic orientation at the time when they cool. And so what we can see here is that sometimes the magnetic orientation is positive and sometimes it's negative. So, what does this actually mean? Well, the only obvious answer that can cause this kind of reversal is that the Earth's magnetic field will occasionally flip. So sometimes north will be north and sometimes south will be south, like it is now. But every once in a while, the magnetic field will flip, and all of a sudden, north will become south, and south will become north. When this happens, the magnetite that's crystallizing will all of a sudden take on a new orientation, won't they? And so what we can do is we can see these changes in the Earth's magnetic field essentially reflected in the magnetite crystals. And so when you pass a magnetometer over the seafloor, you are measuring the magnetite, and when you're measuring the magnetite, you are essentially measuring the remnants of the magnetic field at the time that that magnetite crystal formed. So these black lines represent positive anomalies. That would be when the Earth's magnetic field was as it is now. North is north, south is south. The white lines represent times when the Earth's magnetic field was reversed. That would mean north is south, south is north. So this line here represents the present day spreading ridge where new oceanic crust is being made. And then as we move away from it, we're going to see the same patterns reflected either side. So here's our central point. So we're going to come over here. There's the first. So then we go white. So we have negative, positive, negative. So here we go. We have negative, positive, negative. Then we have another little flip here. So we're positive again. There it is there. Then we go negative again. There it is there. Then we have a big positive event here. And that's it right there. Then we go negative again. Here's the negative portion here. Then we go positive again. There it is there. Then we go negative again. Negative there. Now, then we go positive here. Positive there. Now over here it starts to break up, so we lose it over here. But you can see that the pattern is being mirrored either side of the ridge. So this is showing us that new crust is being made here at the spreading ridge, and then that crust is being split into two. One half goes this way, one half goes this way. And obviously it retains the remnants of the Earth's magnetic field at the time that the magnetite crystal cooled. So here's a more colourful diagram to kind of show you what's going on. So, okay, reverse magnetic anomalies in blue, grey, and this kind of, creamy brown colour. Okay, so that's when north is south, south is north. And then we have normal magnetic polarity, like it is now, north is north, south is south. So what we can see is, if we go back 15 million years, this is where our spreading ridge is creating new crust. And at this period in time, we have a reversed magnetic polarity. North is south, south is north. Okay, and so as this new oceanic crust forms, it locks in that reversed magnetic polarity. Then what happens is this rock that's created, it gets split in two. One half goes this way, one half goes this way. And then eventually the Earth's magnetic field is going to flip, and all of a sudden we're going to have a period of normal magnetic polarity. Then it's going to flip back, and we're going to go back into a reverse magnetic polarity, and so that's when we're going to have this grey rock being deposited, or should I say crystallizing. Then once again, that's going to be pushed laterally. One half goes this way, one half goes this way. Then we have another flip again, back to a normal magnetic polarity. And then we have a flip back to a reverse magnetic polarity, where once again we have the blue coloured basalt now forming. So this is once again, north is south, south is north. And all of these magnetic signatures are being locked into the magnetite crystals in the basalt. And so once again, this basalt here on this side gets pushed that way. This basalt over here gets pushed this way. And of course it takes the remnants of the magnetic field at that time with it. And then here we are in the present day, where we have a normal magnetic polarity, so north is north, south is south, and so the new oceanic crust being created here has this normal polarity. And so when we look at it, when we look at the seafloor and we pass a magnetometer over it, what do we see? Well, we see these changes in the magnetic polarity. We see these anomalies. When we have a normal magnetic polarity, we have a positive anomaly. And when we have a reverse magnetic polarity, we have a negative anomaly. So we can see this is the present day, so normal. Then we had a reversal, so negative, normal, reversal, normal, reversal, normal. So we can see these changes in the Earth's magnetic field in the rocks of the seafloor. It also shows us that because we can see the same rocks either side, or same bands of polarity either side, it means that new crust must be being created here, and that new crust must be pushed laterally away from the ridge over time. So this is solid evidence to show us that the oceanic crust is moving. Now, here we have a diagram of the situation over in the Fuku plate. Okay, so this is the Fuku Ridge. So here's British Columbia, Canada over here. We have Washington State, Oregon, and down into California. So the dashed line here represents the active ridge where crust is being made. And once again, you can see, now in this case, the diagram has even more information because it's been color-coded for us to show us the age of the crust. So we have crust which is 10 million years old, are kind of in these blues and greens, so over here. Then we have about 8 million years old, are in the greens. 6 million years old, light greens, Then we have 4 million years in the light oranges, about 2-3 million years in the medium oranges, and then 1 million years or less in the very dark orange reds. And so once again, what we can see is we can see that over time new crust is being made at the ridge and it's being pushed laterally away from that ridge. Okay, so we can see not only that the crust is moving laterally, we can see how fast it's moving, but the other interesting thing we can see is we can see we have this old crust over here, but we don't have it over here. It's gone. One thing we do have here is that running down through this area here, there is a trench. So we have a ridge where crust is being made and a trench which shows us where the crust is being destroyed. And so the oceanic crust that's being made is subducting underneath North America. So this backs up Henry Hess's model perfectly. And if we look at it on a global scale, here's the same thing. So we have new crust is marked out here in the hot colours, so oranges and reds, and old crust is marked out in blues and purples. And what you'll notice is where we have these spreading ridges, these areas where the seafloor is 1.5 kilometres higher, well, those are areas where we have the youngest crust, and that quite clearly shows us this is where new crust is being made. And we can see the age of the crust increases as we move away from the ridges. So old crust is being pushed laterally away from the ridge. As more new crust is made, it pushes the old crust out of the way. And so we have this pushing force that's going to encourage the continents to move. So, with the exception of, showing us that new crust is being made and old crust is being pushed away from these ridges, can this, can the magnetism of rocks be useful in any other way? And the answer is yes, very much so. So a few slides ago, you might remember me having touched very quickly on the fact that the angle at which the Earth's magnetic field intersects the Earth's surface changes as you go from the equator to the pole. So what are we looking at here? Well, here we have two lines, one in green, one in red. And so these represent samples of rock from Europe in green and North America in red. And they've been taken, well, these rocks are 500 million years old, 400, 300, 200, 100 present day. And so they've taken samples of rocks which are the same age from both continents, and what they've done is they've used the angle at which the Earth's magnetic field, they've used the angle of the Earth's magnetic field at those times to try and work out where on the surface of the Earth they were located. So in the case of these samples that were 500 million years old, we can see the magnetic field is kind of coming in this direction here. It's moving towards the top right. 400 million years, the Earth's magnetic field is coming in perfectly level. This means 400 million years ago, both Europe and North America were at the equator, because at the equator the magnetic field is going to come in perfectly horizontally. Then 300, 200, 100, we can see the angle is steepening. And this is showing us that Europe and North America are moving towards the North Pole until they eventually make it to their current position. So by using the magnetic information in these rocks, it's showing us that the continents are moving. So this is an extra piece of information. I've just been telling you that the oceanic crust is moving, but this piece of evidence shows us that the continents are also moving. But it gets even better, because if we take these paths which we can plot using this evidence, and we subtract this area in between them here, so for instance from there to there, this area here represents the Atlantic Ocean. If we get rid of the Atlantic Ocean, well, what happens? All of a sudden the paths taken by these two pieces of continent overlap. They lie on top of each other. This suggests strongly that North America and Europe were moving as one unit. Okay, so before the Atlantic Ocean formed, it suggests that North America and Europe were joined together as one landmass and they were moving as one. And then when the North Atlantic started forming, they started getting pushed away from each other. So you know, this once again, very, very strong evidence to show us that the continents are moving. Okay, so this is a good place to stop. So once again, stop the video, get up, have a walk around, get a glass of water, a cup of tea, take a few minutes to relax, and then please come back for part 3.